Hello, everybody. Welcome back to Mathlete's Corner. We're 5 questions into the test, and we're starting to get a feel for how this is going to go. So let's keep it moving with problems 6 through 10 from the 2024 AMC8. Problem 6. Sergi skated around an ice rink, gliding along different paths. The gray lines in the figures below show 4 of the paths, labeled P, Q, R, and S. What is the sorted order of the 4 paths from shortest to longest? So the natural thing to do in this problem is take 2 of these paths and start comparing them. So let's do that right after I zoom in a little. There we go. So the 2 simplest paths to compare seem to be P and S. So let's compare those. We'll label P with red and S with blue. So the first question we ask ourselves is, what's different about P and S? They both have the arcs, but P has these horizontal lines, whereas S has these diagonals. So essentially, we're just comparing red to blue. So let's draw one of those red lines on S. Now, if we draw this right triangle, we'll notice that red is a leg of the right triangle, whereas blue is the hypotenuse. So blue is longer than red, and that means that path P is shorter than path S. So let's write that down. P is shorter than S. All right, so let's clear things out now. Now let's take a look at P and R. So once again, we'll ask ourselves, what's different between these 2 paths? Well, P has these arcs on the outside, whereas R has straight, rigid lines. So there are some critical points in R that aren't in P. So let's label those 6 of them. Now let's add those points to P. All right. Now, between 2 of those critical points, which path is shorter? The path demonstrated in R or the path shown in P? Well, the shortest path between 2 points is a straight line. So path R, for example, if we choose these 2 critical points, path R has a shorter path than path P because path P is more curved instead of a straight line. And this is true for every pair of consecutive critical points on path R. So let's note that wrong color. R is less than P. Now, we could take a look at path Q and start comparing them to R, P, and S. But we could notice that the only answer choice that has R, P, and S in that order is answer choice D. So we can go ahead, bubble that in, and move on to the next question. Problem 7. A 3x7 rectangle is covered without overlap by 3 shapes of tiles, 2x2, 1x4, and 1x1, shown below. What is the minimum possible number of 1x1 tiles used? So this is an optimization question, and when it involves rectangles, it's probably a good idea to start by finding the area of each tile. So let's just write those in. And the area of this rectangle, well, it's a 3x7 rectangle, so it has an area of 21. So We'll notice that these two tiles have the same area, which is 4. So as we use the tiles, we take away 4 from the area of the big 3 by 7 rectangle. So the number of tiles remaining is the number of 1 by 1 tiles that we use. So that number can be 21, firstly, or it can be 17, or it can be 13, or 9, or 5, or 1. So we'll notice that we can knock out options B, C, and D because the number of 1 by 1 tiles used can only be 1 or 5 from this list. So at this point, you're in the test, you want to get this question over with. You could just guess A or E and move on, but it turns out that it's not as difficult as it seems. So you may try to experiment to try to find if it's possible for one tile, one by one tile to be used. And you'll notice that it's hard to do that. And that's because it's actually not possible. And we're going to look into why. So notice that in the 3 by 7 rectangle, the number of tiles in each row is 7, and 7 is odd. But in the 2 by 2 and the 4 by 1, or 1 by 4 rather, the number of tiles in each row that's used is an even number. So that means that you need to use at least 1 by 1 tile in each row. So you need to use at least 3, and 1 is not possible. And we can bubble in E and move on. Problem 8. On Monday, Tay has $2. Every day he either gains $3 or doubles the amount of money he had on the previous day. How many different dollar amounts could Tay have on Thursday, 3 days later? For this question, there might be something clever, but it's not obvious. So a small tip for the AMC8 is when you're in the early questions, if it's a question that seems kind of bashy, but it's not too much, then just go for it. Don't try to find a clever solution. So in this case, we're looking only at 3 days, so we can just look at every possibility and we can just count our answer with our fingers. So we'll label gaining $3 with a 3, and we'll label multiplying by 2 with a D for double. So he starts with $2 and we're thinking about 3 days. So the only possibilities are 3, 3, 3, and D, D, D. Now remember, he starts with $2. So if he gains $3 every day, he'll be left with $11. If he gains $3 and then $3 more, then he'll have $8. Double it, and you get 16. 2 plus 3, 5, times 2, 10, plus 3, 13. 2 times 2, 4, plus 3, plus 3 is 10. 2 plus 3, 5. Double it twice, and that's 20. 2 times 2, 4, plus 3, 7, times 2, 14. 2 times 2 times 2 is 8. Add 3, and you get 11. 2, double it 3 times, and you get 16. So you can see here, it wasn't that much work. So it's probably a better solution to just go through every possibility and quickly figure it out. So in this, we have 2 11s, so we'll remove one of them. We have 2 16s, so we'll remove one of them. And that is all. So we can just count up the solutions. 1, 2, let me actually show my counting. 1, 2, 3, 4, 5, and 6. So there's 6 solutions. We can bubble in D. Keep going. Problem 9. All the marbles in Maria's collection are red, green, or blue. Maria has half as many red marbles as green marbles and twice as many blue marbles as green marbles. Which of the following could be the total number of marbles in Maria's collection? So, this is a very openly algebraic problem. So, let's start by assigning variables. Let's say the number of red marbles is R. Since there are half as many red marbles as green marbles, the number of green marbles has to be 2R. Now, we were also given that there are twice as many blue marbles as green marbles. So the number of blue marbles has to be 4R. So the number of blue marbles is 4R. We can add all of those up to get 7R as the total number of marbles in Maria's collection. So all of the conditions can be satisfied as long as the total number of marbles is a multiple of 7. So we can bubble in E and keep it moving. Problem 10. In January 1980, the Mauna Loa observation recorded carbon dioxide levels of 338 parts per million. Over the years, the average carbon dioxide reading has increased by about 1.515 parts per million each year. What is the expected CO2 level in parts per million in January 2030? Round your answer to the nearest integer. So in this problem, we're given a start point and a rate per year. So we can start writing, or start constructing rather, our equation. And we'll leave an open parentheses for the time gap. And we're also given the start time and the end time. So from 1980 to 2030, there's 50 years. So we can write that in. And this expression that we have here is exactly what the problem wants us to evaluate. So this is just 1.515 times 100 times 1/2. So that is 151.5 times 1/2. So that's around 150 times half, which is 75. And then the 1.5 times half would be 0.75. So it's 75.75. Now, remember, we want to add 338 to this. And we also want to round our answer to the nearest integer. So we'll add 338 to the closest integer to that number, which is 76, and that gives us an answer of 414. So we can bubble in option B. That's all for this video. Thank you for watching. Don't forget to hit that like and subscribe button, and we'll see you next time here at Mathlete's Corner.